Thank you very much for the kind introduction. So first of all, I've realized that I'm the only speaker today who is not wearing a suit. But then, again, I'm a physicist, so I can't excuse myself. That's just like fulfilling of stereotypes. And I have the challenging task now to talk to you about our work in the field of quantum mechanics. So first of all, I should actually, oh, this is very weak. I should actually tell you what is a quantum spin liquid, because that's big written in my title. So what is a spin liquid? A spin we know as an intrinsic property of the electron, because the electron has a charge, and it is spinning around an axis. It creates a intrinsic magnetic field, and this small amount, this quantum magnetic field, we usually denote by an arrow. Here it's this kind of a pink arrow, and this property we call a spin. Second part of the name is what is a liquid. That's a bit easier to digest. This is just a picture of water. So if I combine these things, I end up with the picture of my title, a spin liquid. So we have spins in this picture on a liquid or in a form of a liquid. What that means is a liquid is a phase which is long-range entangled, but not long-range ordered. So in contrary to a gas or a solid, these spins behave like a liquid. And what that means, I will tell you in my talk now. So for me, working in the field of magnetism, a spin liquid is a new, novel, very exciting new magnetic phase. It's just been discovered experimentally within roughly the last 5 years in a few compounds. And because it is like water, it is a dynamical down to, theoretically, even down to T equals 0, to the absolute zero temperature. And in contrary to a solid, it doesn't break any symmetries. That's what makes it exciting for us. So as I already said, it's in stark contrast to a solid. So conventional magnets, we have a ferromagnet and an antiferromagnet, where in the ferromagnet all spins point in the same direction, and in the antiferromagnet on the right side, they point in opposite directions. These phases, as you see, they break spatial symmetries because of the regular arrangement of spins, and they have long-range order, which usually appears at a temperature which is correlated to the intrinsic energy scale in a certain material. So how does a spin liquid emerge? How do we end up in this new magnetic phase? I'm talking to you now about something we call geometrically frustrated magnets. This sounds surprising to a lot of people I talk to who don't work in this field. And how I want to introduce it is with something called the love triangle. So in this love triangle here, we have these 3 hearts. And if all these 3 hearts are all mutually in love with each other, Hollywood tells us that at some point one of them will be frustrated. And this same picture of the triangle, we can now put now our spins on them. So what I will now assume is that these black lines here, they are antiferromagnetic couplings. From the slide before, you remember antiferromagnet means they should point in opposite directions. So if I put a spin there on the lower left corner, since this black coupling is antiferromagnetic, it means that the upper corner spin has to point down. But then there's the right heart left on the right side. So in relation to the lower spin, it should point down because it's antiferromagnetic. But now you see in the relation to the upper spin, it should actually point up. So this third spin doesn't know what to do, and this is what we call a frustrated magnet. So this part where it doesn't know how to decide between the 2 possible options. However, nature is a bit more clever. What actually happens if you have this situation and you allow the spins to rotate freely in this 2D plane, which we call Heisenberg spins, then what you actually will develop, what I show on the bottom left, is like this 120-degree structure, which is a compromise between minimizing the frustration. How can this be realized in lattices? So some established candidates are first is a lattice we call triangular lattice. So we take a lot of these triangles and now we connect them by their edges. And this creates a lattice. And here exactly observed what I showed you before. They order in this 120-degree structure, which is the compromise. Another lattice, which is realized, we call the kagome lattice. Kagome is actually a Japanese word, and it's a structure how to wave a bamboo basket. And the lattice actually has the same structure, so the triangles here are now corner sharing. Left side, there are edge sharing, there are corner sharing. Because a corner sharing arrangement increases the frustration, this is a prime candidate for a spin liquid ground state. So when you put your spins theoretically on this lattice, they will not order down to T equals 0. And the word quantum in my title comes because if you go to the lowest possible possibility, so if you put only 1 electron at each of these sites, which has spin half. This is the lowest possible spin. And this we call then a quantum spin liquid. So now we clarified the second part of my title, and now I want to talk about the first part of my title, the new physical realization. So we as experimental physicists, we have produced a new compound. It's called calcium 10 chromium 7 oxygen 28, a bit scary formula. And so there's calcium, chromium, and oxide in them. In our labs, we can grow crystals of this material. You end up with these black cylindrical crystals up to a little bit less than 1.5 millimeter. They look pretty unspectacular on a photograph, but for me, a crystal actually looks like that. That's a unit cell, that's the crystal structure of this compound, and there it looks already much more exciting. So now you see we don't have this simple arrangement of just perfect triangles anymore. In reality, things usually are more complicated. So what we have now here is the balls. There we put these are chromium 5+ atoms, so they have one electron in the outer shell, so they actually have this spin half small magnetic moment. And now they are coupled with a lot of different interactions paths. They're actually up to 7. They are shown by the different colors and labeled with the different J numbers. And this gets rather complicated, but when I take this black dashed box and extend it in the AP plane, that was the wrong button, we get this structure, and now if you think back to slides there, I showed to you this Kagome structure. And this is what I actually call the Kagome bilayer model. So this resembles one of these frustrated geometries where a spin liquid ground state is thought to be possible to be realized. So in this material, we did a lot of measurements. So we measured specific heat, magnetization, different substitutabilities, muon spin spectroscopy. I don't want to go in detail of all these measurements, but in all these measurements, we haven't seen any sharp features, as you also see in this kind of overview. So, as I told you before, if you have a long-range ordered classical magnetic phase, you break some symmetries. Symmetries and thermodynamic measurements show up as sharp features. We didn't see anyone. And in particular, we measured down to 20 millikelvin, I wrote it here. So 20 millikelvin in centigrade, it's minus 273.17 centigrade, and the absolute 0 point is 273.15 centigrade. So, of course, in the lab, we can't go to absolute 0, but we can go very close to it. And we haven't found any sign of this classical ordered magnetic phases down to this temperature. Further, we found that in this compound, we seem to have ferromagnetic and antiferromagnetic, so both kinds of these interactions. No magnetic anisotropy, so that means the spins can actually rotate as they want. And in the right side, I show you that we found a lot of evidence that in the gray shaded region, which is between 300 and 500 millikelvin, we found a crossover into this spin liquid phase, which has this dynamics in the ground state. To elaborate this ground state further, we went to inelastic neutron scattering, as it was introduced that we work with neutron scattering. So that was what I show you here is powder data, and you see that this is energy transfer versus wave vector transfer, so these are magnetic excitations measured with inelastic neutron scattering. And you see that there are two regions of scattering. I indicated it by the black dashed lines. And we then looked at this bilayer again. These two regions come from the two layers. We can also do single crystal inelastic neutron scattering, and this data I've shown you now shows wave vector transfer in this Kagome plane on the lower left corner. And this data is taken at two different energy transfers, so the lower one is the lower excitation region, the upper one the higher. And we see this diffuse ring-like scattering, so this doesn't explain much to you, I guess, but we can, for example, compare it to Herbert-Smithite, which was 5 years ago, 2011, the first compound which, 2012, sorry, the first compound which was generally believed to realize the spin liquid ground state. And you see that we have similar features. So we have this small ring-like scattering in the lower band and the large rings in the upper band, which are comparable to this other spin liquid compound. Analyzing inelastic neutron scattering, which was done at different ambient conditions, like higher magnetic fields, we could estimate our Heisenberg Hamiltonian. So this is the only equation I have in my talk. And the Heisenberg Hamiltonian basically describes how all these different colored couplings are shown to you in the crystal structure, which values they get. So how strong these spins are coupled with each other. And what we realized then is a very surprising result. So I've shown to here the same colors as before, and this is the color-coded this model of the magnetic coupling, calling the Kagome bilayer. We saw that the green triangles here, they realize FM ferromagnetic interactions, while the blue triangles, they realize antiferromagnetic interactions, and this red short bond, which couples two triangles which are on top of each other, also becomes weakly ferromagnetic. So we were surprised because there's a lot of ferromagnetism, but as I showed you before, if you put 3 ferromagnetic spins on a triangle, they can order. There's no constraint. So the frustration in this compound comes to a very particular arrangement of these triangles. Because if you see here in this dashed box, you see that there's always a green triangle on top of a blue one and vice versa. So now, if we put the green triangle, where all spins want to point in the same direction, on top of this triangle, which is antiferromagnetic, so it would realize this 120-degree structure, we see that actually here, we have a problem. When they point in the same direction in one corner, the other 2 corners actually can't realize the desired direction, because the red interaction wants to make them point in the same direction. And this is where we get the frustration in this compound. And this is the new frustrated motif what we found. So to sum up, this new compound, calcium chromium oxide, we could show by our measurements that it fulfills all the required conditions for this new spin-liquid ground state. And further, we could actually pin down the reason why it doesn't order in these non-magnetic phases, but develops this exciting new magnetic phase. And the reason is that we have these 2 triangles. Actually, we have 2 of these love triangles coupled to each other, which is even higher degree of frustration. With this, I want to finish my talk, and I will be most happy to answer all your questions.